All right, welcome to the HPC track here at Open Compute. My name is Steve Roberts. If you haven't seen or heard from me before, I'm a little bit sad about that because we're hoping that all of you will join the project meetings and we can work the project charter together. That project charter is in redefinition. Originally, there was a grand vision for this group to revolutionize HPC. That vision didn't really materialize. About a year ago, I came on board, and we ran the track last year with the idea that we would take some of the submissions going through the pipe and redefine that charter. So it turns out that most of the submissions are going through Rack and Server Group, and in talking with the CTO of Open Compute and about the continuation of this particular project, he advised us to go forward with a new charter in mind, being to represent the HPC community and look at things that, at how specifically the Open Compute technology either applies or doesn't apply to what's going on with HPC procurements. And so towards that, we're going to start to look at some of the larger procurements and map HPC OCP offerings to that space and look at the winner of the space and start to provide some feedback to the data center manufacturers as to where the efficiencies are and where this Open Compute communities, the various Rack and Server Group, et cetera, where they should consider focusing some more contributions to get a broader appeal into HPC for the product set. That being said, Sidney Mair is here with a success story for Open Compute in HPC data centers. And so it's nice to be able to kick off with a representation of how this is done. And then as we build out the charter and work through the project teams, we'll refine how we steer the various other OCP committees to making this a higher probabilistic event. So with that introduction, let me turn you over to Penguin Computing's Sidney Mair.
Thank you very much, Steve. I appreciate it. Good. Welcome. Thanks for attending. Let me ask you, in the room, how many people in the room are actually in the HPC market space, high performance computing market space? So pretty much everybody is. Can I create a definition of that? That's right. And where does AI fit in the HPC space? That's an interesting discussion because we're finding that kind of almost a bifurcation on what artificial intelligence, the orientation of artificial intelligence implementations, either machine learning or deep learning, actually occurs within either the HPC space or more in a scale out or traditional server-based space. So it kind of crosses both boundaries. And it's really interesting in the marketplace itself. There's a lot of discussion about where does certain parts of AI fit in that space. And we've done a number of solutions that actually integrate both your deep learning, machine learning environment into an AI or an HPC-oriented approach to computing. So high-performance computing, most people think of high-performance computing as generally a physics-based computing environment where you need to be able to scale to large numbers of cores in a single job or application to be able to get some type of information that you'd like, some result on some scientific information. In the case of machine learning, you're trying to either train or infer what you would like to be able to look at as what's happening around you, right? And that's done more through data rather than through physics. It's really kind of, when you look at both of them apply to what we're going to talk about today. So Penguin Computing, I don't know how many people know much about Penguin Computing. I don't know. the title of this is How Open Technology Helped the DOE Labs Place 16 Supercomputers in the Top 500. And I'll talk a little bit more about that in a few minutes. Man, this thing moves fast, doesn't it? Doesn't want me to describe our company, does it? There we go. We'll talk a little bit about Penguin Computing. Penguin Computing was originally formed around open computing technologies. When Linux started emerging back in the late 90s, Penguin Computing was formed to provide Linux solutions. At that time, we were more like a systems integrator. We would take existing environments, put them together with a software stack, and provide it out to our customers an integrated solution. That evolved over the years. We acquired some technologies like a technology called Beowulf, which was originally developed by NASA and several other organizations. We bought that technology and then gradually built ourselves more into a high-performance computing company as well as a data center type company. We basically take leading edge design, implementation, hosting, and managed services to provide a capability to our customers to allow them to be successful in their vision or missions. We've got more than 2,500 customers in 50 countries, and to date we've put in well over now 300 OCP racks in the marketplace based on this Tundra extreme scale design that I'm going to talk about today. OCP Clusters in the top 500. Since 2016, we were awarded a contract in late 2015 from the DOE. I'll talk about the contract itself in just a minute. We've built over 35 large OCP systems ranging from about a half a petaflop of performance to now over 6 petaflops of performance into the program. And over that time, 16 of those systems have been in, most of them actually in the top 250 of the top 500, some of them in the top, about probably 4 or 5 of them at one time or another were in the top 40 of the top 500. And gradually they move up over the years. Every 6 months that list comes out. The implementation is part of the DOE's Advanced Simulation and Computing Program. It's actually part of what's called the NNSA, which essentially is our nuclear stockpile verification environment. It essentially simulates every nuclear device that we have to make sure that those are viable devices to continue to utilize in the future. And they have to do that every year. So there's a series of codes that they use to do that. The contract itself is called Commodity Technology Systems 1. This contract has been around for a while. This is actually, I think, about the 5th iteration of this contract. And what the DOE does is goes out and competes this contract about every 4 years to deliver their production environments for the NSA and the nuclear stockpile assurance. To date, we've delivered over 30,000 nodes in the environment. And actually, it's not just Broadwell and Skylake-based nodes, but as well as AMD, the new AMD EPYC Naples nodes as well in one of our latest deliveries to them. Basically, the contract, the way it's written, is it's a not-to-exceed contract of about $250 million over 3 years, and it's whatever systems they need to buy at the time. But one of the things I think this exemplifies is how you can take open environments like OCP and create things that can give organizations both value and performance. And this is kind of a statement. Let's see if this works. There we go. This thing here is actually a statement that was made by one of the program management staff within the CTS1 contract, that by moving more and more toward open systems, they've been able to transition from about 100 million per teraflop in 1995 down to about 5,000 dollars per teraflop in delivering HPC compute cycles to the need. And that's probably, you could do many different types of calculations, but that's a pretty good order of magnitude if you look at it, just by moving toward both open systems and commodity type environments. So what's different about the Tundra design? The Tundra design is an OCP inspired environment. It uses a standard OCP rack with your 12 volt bus power supplies. In one rack, we basically do a shelf that has 3 nodes in it. In one OU compute shelf, supports up to about 102 nodes in a single rack. So if you think about it in the data center wise, most data centers are 14, 15 kilowatts a rack they may provide or whatever. We're reaching upwards of 52 kilowatts a rack in the environment. So if you're thinking of how do you place one of these things in a data center, you've got to consider that when you're getting this kind of a density in an environment. We have high-speed, low-latency interconnects, InfiniBand, OPA, multiple different types of InfiniBand. The latest deliveries we're making to them is HDR from Mellanox, and most of the systems here were based on OPA 100 from Intel. We do both air and liquid cooling in the environment, and the liquid cooling is both direct-to-chip or rear doors. With a combination of direct-to-chip, rear doors, and direct-to-chip and rear doors, we can essentially get to a room-neutral environment in the rack or within the data center. It's accessible via cloud through Penguin Computing on Demand. We actually use what we build. Penguin Computing on Demand is a cloud-based HPC environment, and the Tundra is what we use for our implementations of that cloud. And then you've got multiple storage options, multiple file systems that are available to you. If anybody has any questions on file systems or whatever, I'd be happy to answer those as well. All right, so how do we do it? You have the 3 12-volt bus bars within the rack, and then you add a power shelf. In this case, we're showing our Vertiv power shelf. We also have a power shelf from Bell that's configured slightly differently. You have multiple options for connecting to your main power, so it could be 208. 277 480, there's probably about 8 different types of power we can bring into that shelf or more. There's a list here of some of them. You can do redundant power, both AB power as well if you need it. It provides, like I said, 3 pairs of DC output bus bar connections on the back. It actually gives you the ability then to do hot swapping on your nodes. So if you have failures in your nodes, you don't necessarily have to bring the whole rack down. You can hot swap the individual nodes. And then in this case, this power shelf also has, if you have AC equipment that needs to go inside the rack, there's also convenience connections for AC for certain types of switching. What's a node look like? Each node is 1/3 wide. And you fit 3 nodes in a shelf. Each one of these nodes are 2-socket environments that allow you to get the density that you kind of want in the environment. There's also options for storage nodes, which includes a single socket and up to 8 disk devices as well. There's a number of other combinations. There's probably about 8 or 9 different combinations that you can put into this environment right now, including GPU accelerators, as well as AMD, ARM, and as well as other options as far as networking, et cetera. This is an example of our GPU environment. It's a 2-node sled. This sled is all the way across 1U, and has 4 GPUs. Can either be attached PCI or an NVLink attachment, whichever one you want, SXM2, and there's several other combinations that you can do with that as well. Doesn't necessarily has to be GPUs. It could be other forms of accelerators if you wanted to in the box. Here's a list of the major systems we delivered to the DOE. That nomenclature here, oops. The nomenclature here, we deliver them in what's called scalable units. So a scalable unit is essentially a 4-rack environment that has 3 compute racks and some other infrastructure rack beside it. And so when you see 1, that's 4 racks with that one. 14 would be 4 times 14, or, you know. So, you know, you can see the number of large systems we've put together. Anything over 4 has been on the top 500 list at one time or another. Our latest delivery, which is this right here, which they actually don't have the official name for it yet, or it's not announceable, so we just use a little parentheses H on it. That is an 8SU Skylake environment, again, based on OPA. If it says LC on it, that means it's liquid cooled. So we have a combination of both air-cooled and liquid-cooled environments in here. They're close to 50-50, or if you talk about total number of racks, probably it's about 60-40, 60% liquid-cooled and 40% air-cooled right now. So, all right, so this is one of the larger systems, or list of the larger systems we put on. Quartz at one time was number 30 on the top 500 list. It is actually being enlarged by an additional 2 SU, so it's going to become a 16 SU system coming up, which will put it somewhere around a 5 petaflop machine. Jade, each of these are large systems that we've placed in-house. Some of them are GPU-based, where we put GPU-based systems. Some of the GPU-based are upwards of 6 petaflops, depending on how you want to calculate that number. One of the newer systems that we put in, it was just delivered a little over a month ago, is a system we call Corona at Lawrence Livermore. That system is an AMD EPYC-based system with AMD Radeon GPU accelerators. It's about half populated with GPU accelerators, and the other half will be populated with the next generation of their GPUs instead of their first generation GPUs that it currently has in it. Currently is about 4.2 petaflops of machine, and by the time we're done, it should be more than double that in the environment. Vega 10 and Vega 20. It's a good way to put it, yeah. They actually have a different name for them as actual products, but you can use those. Yeah, yeah. Actually MI60, and I don't think they've actually announced the name of the Vega 20 product name. What? No, they're Vegas. Yeah, yeah, yeah. Okay, I think that's about where we're at. I'd love to answer any questions for you. And I happen to have Phil, our CTO, in the room, so if you got technical questions, I can always get him to answer them too. So, yes?
My understanding is there's been quite a few lessons learned. Could you maybe cover some of those?
Sure. Wow. There's always lessons learned, right? Especially when you're doing an HPC environment.
If you were Lawrence Livermore National Lab, what would you do different now?
What would you do different now? Well, you probably need to ask Lawrence Livermore, but we can give you some experience. Our first round of liquid cooling, okay, we worked through a lot of challenges with the direct-to-chip liquid cooling. And so we've had some engineering design changes on some of the liquid cooling. We were basically the first organization to implement OPA. So we delivered some of the first large OPA systems at scale. We had a lot of challenges with OPA in the beginning, especially the cabling. And one of the things I would like to mention is when you're doing optical cabling and high-speed interconnect, you've got to be very careful on the quality of the cabling. And if you choose the cheapest cable, guess what? You get what you ask for. Because we've done some large-scale cable replacements on some of the early systems. Now it's pretty stable, et cetera. A couple other things. When you think of OCP and you think of someone going into a traditional HPC environment, especially like a lab where you have a unionized environment where people that touch those machines or need to do work, electrical work, et cetera, they have specific specifications. And by the way, all three of the major labs have different specifications in different groups. So when you look at an OCP, you've got 3 bus bars in the back of that rack. Those 3 bus bars, when you look at it for someone that doesn't fully understand what it's doing, the first thing they think of is that's a hazard, because you got three 12-volt bus bars sitting there that if someone reaches into the back of the rack and takes a screwdriver and puts it across there, you're going to get a pretty good jolt that happens. It's probably not going to kill somebody, but it sure can cause some big problems. So we had to overcome some of those discussions with them to show how the safety of that environment looked, and we've done some things to the back of the rack to make sure it makes it harder for somebody to get to it. Now, the good thing about OCP is you don't have to get to the back of the rack to do anything. Everything's in the front. All your connections, any work you have to do on a node, if you've got to do maintenance, it all slides out from the front. So you never have to get in the hot aisle. That's probably one of the big advantages that have turned out in here, because if you walk into some hot aisles of an HPC data center, you sit in there for more than 5 or 10 minutes and you're cooking. It's pretty hot. So if you can do all your maintenance from the front side, do all your cabling from the front side, you do everything from the cold aisle, it's much more effective than having to sit there and work on a machine back in the backside of a hot aisle in order to get access to components, et cetera. We had we had a couple issues with the Vertiv power supply, the rectifiers that had to be retrofitted basically during the program that was discovered. One of the big ones, this is an interesting one because you love the lessons learned. On a typical 19-inch server that the power supply is in the server, Intel or whoever's designing that 19-inch server, they have a connection to the CPU, and if the CPU starts exceeding the power capability in a spike of that power supply pulling it in, it automatically throttles that CPU down. And a lot of times people don't notice it unless you're in the HPC business, then all of a sudden you notice that your performance has gone way down. Well, one of the advantages and the disadvantages of this design is you don't have that. So we can run, we can run basically at full speed continuously. However, when you're doing an HPC code that does a full MPI across the entire cluster at one time and basically stops, in other words, brings all the power usage down fairly low, and then all of a sudden all the processors kick back up 100% at one time, that power curve of bringing it up, when we first started doing that, the first test, actually Sandy is the one that found this, is it brought down the system because the bus bars couldn't come up fast enough in order to meet that power ramp. So we added what's called a capacitor shelf in, and that capacitor shelf took care of that thing, and then later on the rectifier software was modified and that design was modified so that you get the proper ramp up. And I don't know if I described all that properly, but that's as much as I can probably describe on that. I'm not a power person. Yes? They're cooled by fans inside the inside the rack. So the rectifiers don't produce that much heat. They're very little heat built up by the rectifiers themselves. It's really the nodes by far generate a lot more heat. So in this case, we don't do, in the CTS contract, we don't do anything that's close to room neutral. We don't do any liquid-cooled, chilled doors on the back. It's, all of it is direct-to-chip liquid-cooled. It takes out about 70% of the heat, depending on what we're running on the system, okay? Now, there are some other things that we think we're going to get additional information on. Tell me when I run out of time, by the way. Over time, we expect to get some better information about liquid-cooled versus air-cooled as far as the reliability of those nodes. Because we have so many systems that are both of them, and we're collecting data on RMAs and those things that are coming back to try and see if the liquid-cooled actually is more reliable because you don't have huge swings in temperature. It stays pretty much constant. The other thing it does is it can stay in turbo mode much longer, and you don't get one node going out of turbo mode versus another node in turbo mode, and then you end up with a reduced performance on your application itself, because the liquid cooling keeps everything pretty much consistent. So, any other questions?
Yes. So if you could pause just for a second, so if the next presenter could come up and
get started, we can.
while you finish the questions, that would be a better answer.
Yeah.
How much better can you do with liquid-to-chip and rear door than just one?
Then just what?
Than just one of the two?
Well, about somewhere between 60 and 70%. I'll go ahead and disconnect and everything for you. All right. About 60 to 70% can be pulled away from direct-to-chip liquid cooling, and and the only thing we liquid cool on that is the socket itself, the CPU. Okay. If you add a chilled door to it, we take out the last 30% with the chilled door. So you basically can get to 100% room neutral in the environment. Now, a couple things you got to think about with OCP, because OCP, the specs aren't necessarily there to make sure those racks are fully sealed and those racks will not leak air, you could say. So you got to do some extra work when you go to put an HPC system together, so that when you're putting in either blanks or you're putting in nodes and everything else, that your airflow is designed such that you can get to completely room neutral. There's a little bit more work to do on room neutral type of environments. Yeah. Okay. Yeah, Bob.
So operational efficiency. So OCP, sort of standardizing various things. So lead times reduced, cost savings, or maintenance improvements. How were those things impacted?
Well, I think maintenance improvements. There's a lot of advantages on the maintenance side, because you're working from the front. They're all field replaceable units. So when you spare or you do things like that, and you want to keep a cluster up and running, it's very easy to hot swap a sled out and get that node back up very quickly. In most cases, we do diskless nodes, and we're doing, Pixie booting and things like that nowadays. To do it, we don't put a disk in the system, but many of our customers do require a disk in the system as well, but it just varies by customer on what they want to do. But usually we use a head node and a management node and login nodes to take care of that. Some of them, sometimes they're combined into one, but just depends on how large it is. Yeah. All right, if anybody has any additional questions or wants to talk, I'll be happy to step outside and talk further.
Let's step outside.
Let's step outside. Yeah.
Sounds obvious.
Yeah, thanks.
Thank you, Sid. Appreciate it.